Hi, my name is Mr. Evangelista, and in this episode, we're going to be looking at a problem where a car is doing a circular orbit inside a frictionless cone. Let's read the problem. Consider an object of mass m that moves in a circular orbit with constant velocity v along the inside of a cone. Assume the wall of the cone is frictionless. The cone makes an angle phi with respect to the vertical axis. Find the radius of the orbit of the object in terms of the given information. So let's take a look. The first thing we should do is we should draw a free body diagram. So here's the cone, here's the car going in a circle around the cone. We've got the force of gravity downward, and we have the force normal perpendicular to the surface of the cone. Now let's redraw the free body diagram and break the forces into its components. Force of gravity is good, it's in the y-axis. Force normal, however, is kind of at this angle, so we need to break it down into its components. This is the angle phi, and so we can break the force normal down into an x and a y component, where the component that is adjacent to the angle phi will be the cosine, and the component that is opposite the angle phi is sine. We're going to clean this up a little bit. We're going to get rid of the force normal, and we're going to move the arrows so that they're coming from the object itself. So here's our final free body diagram. We've got force normal times the sine of phi going up, force gravity going down, and force normal times the cosine of phi pointing towards the center of the circle of the cone. Notice that the force of gravity and the force of normal sine phi are equal, and this means that the object or the car will not accelerate upward or downward. The forces are balanced. So let's sum the forces in the x and the y direction. Remember, we are trying to solve for the radius of the cone. So here's our free body diagram for reference. Let's do the y direction. We know that force equals ma. So we have force normal upward, force normal sine phi upward, minus the force of gravity, which is downward. And that equals ma. We replace force of gravity with mass times gravity. And remember, the acceleration equals 0 because it does not accelerate upward or downward. And so we can replace the right side of the equation with 0 and get that force normal sine phi equals mass times gravity. Now let's do the x direction. We have the sum of the centripetal forces equals mass times the centripetal acceleration. The centripetal force in this case is the cosine of the force normal, and that equals mass times the centripetal acceleration. And we can replace the acceleration with v squared over r, and that's where we see our variable r, which is what we're looking for. From this point on, we're stuck. We can't break anything down further. We know that if we look back at our y direction, we can rearrange this equation to be force normal equals mg over sine theta. And notice what happens here. We have force normal in the y direction and force normal in the x direction. So we can take what we solved in the y direction and plug it into what we have in the x direction. So we're going to replace that force normal with mg sine of phi, mg over sine of phi. So replacing it, we get mg over sine of phi times the cosine of phi equals mv squared over r. Now we just have to rearrange this equation so that we isolate r. A couple of things you notice, the m's cancel out, so mass cancels out, that's nice. And again, let's rearrange to solve for r. So a little bit of algebra here, we have r equals v squared times the sine of phi divided by cosine of phi times g. Now, sine of phi over cosine of phi is just tangent of phi. And so here we have our final equation with radius. It equals the velocity squared times the tangent of phi over g. Now, with a lot of these circular motion problems, you also have to be able to write this equation in terms of omega and then in terms of the period. So remember, velocity equals the radius times omega, the angular velocity. And then you can replace omega with 2 pi over capital T, which is the period.